So we cover the steam engine, whereas you extract the heat from the high temperature, and then you create a steam, and let the steam do the work, and then the thing become a liquid, and then come back. This kind of cycle. So now let's look at a refrigerator. So refrigerator is like this. You started with something at a low temperature phase, a gas at a low temperature, and then you compressed it. So you compress it. During the compression, you're going to do some work, okay? And then after you do the work and it's become a higher temperature, if you look at a PV diagram, I'm starting from this point, which is a gas phase. Then I compress it, and this will be a superheated gas phase, high temperature. Then I let it pass through condenser, and this condenser is going to cool it down, cool the superheated gas, and expel a lot of heat into the high temperature reservoir, and then it becomes the liquid. And from liquid going to this, we call the throttling process. And I already covered, during the throttling process, the enthalpy remains the same. So throttling is usually come from something where the intermolecular distance is very small, which is like a liquid or very dense gas at a very high pressure. And then you let it expand into a lower pressure part, and then the thing will cool down. But the interesting part is during the cooling down, the enthalpy actually remain the same. So important part for throttling is your enthalpy is going to equal to these 2 points are going to be the same. So now from this point, then you let it go into the evaporation. So the liquid here is now going to evaporate, and during that evaporation is going to absorb the heat and it become a gas, but the temperature here is going to be the same. So it become a gas and coming over here, and so it will just during this time is going to absorb the heat, and that is your QC. So what is your QC that you extract is your H1 minus H4. Right? This is a high enthalpy because you suck the heat over here. This is a lower enthalpy, and so on. Now, what is then the QH? Which is the heat that you expel? Of course, it's going to be equal to this QC plus the W. That is your QH. But if I want to use this picture, then what is my diagram? It's going to be equal to the H2 minus H3. So if we want to do the coefficient of performance, that is going to equal to the amount of heat you extract from the cold temperature reservoir to the divided by work, and that is also QH minus QC, right? So I can rewrite this one. This is going to equal to what? H1 minus H4, right? Then this is H2 minus H3 and minus H1 minus H4. Okay, so I can change this, and this become plus H4. Okay, but H3 equal to H4 like what we described. So these two. So if I want to calculate what is the coefficient of performance, simple, I can just write it as H1 minus H4, H2 minus H1. So in this kind of calculation, what it involves is you pull out the table, okay, and to see if you can find out what is the enthalpy at the stage 1, and what is the enthalpy at the stage 4, or more likely I should call this as H3, right? Then H2, you don't really kind of, you cannot just directly pull out from the table, just like what we did earlier for the steam engine. What you're going to do is you're going to rely on that this process is actually an isentropic process. So you need to find out, oh, okay, this is the entropy is going to remain the same. Okay, and then from that you will be able to calculate what the stage is. So that is the first part that you need to know about how do we calculate the coefficient of performance for the refrigerator. The next, we're going to go through the specific example, and then to find out how do we calculate that from the table. So now the homework problem said, well, we have a house refrigerant. Use this HFC 130. Refrigerator uses HFC 134A as a refrigerant. Okay, people don't use Freon anymore because of it create the greenhouse gas. So now we use this as a refrigerant. So now it operated. The condition given is operating between 1 bar and 10 bar. So therefore, in here, this will be your 1 bar. And this will be a 10 bar. Okay? So now I know that this one is just at the gas phase. So at this 1 bar, what is the gas phase? So now if you look at the table 4.3, then you'll find out at a 1 bar, okay, so the 1 bar is the temperature is now at minus 26.4 degree centigrade. And it's H1, you can calculate it. So H1 is going to equal to 231 kilojoule. Not only that, you will also know the entropy value. So you're going to need that entropy value in order to calculate H2. Okay, so now I can write down now H1 equal to 231 kilojoule, and S1 is going to equal 0.94 kilojoule per Kelvin. Okay, and remember this is also, this one also specified that its temperature is minus 26.4 degrees centigrade. It's pretty cold, right? So now how do we calculate H2? So the way you can look at is, oh, okay, so now H2, it has a, now this is, I indicated it is a superheated. So you're gonna need to use table number 2, because what this one say is at this kind of at the critical point temperature. So that you cannot use this table anymore because this is just saturated, and what we do it is this really superheated gas phase. So let's look at S2. So this is the one, this is the information we're going to need. So point 2 cannot be at the temperature that it is at the phase boundary between just evaporation temperature. So this is superheated, and now you're going to use this table 4.4. In the table 4.4, this is I want to teach you how to read this, and this one tell you if they are in the gas phase at 10 bar. Okay, so now look at this 10 bar, and that's that, and then it depends on its temperature. It's going to have a different value of enthalpy and the entropy. But we do know that at 10 bar, so we do know S2 is at 10 bar. Okay, we also know that S2 has to equal to 0.94 kilojoule per Kelvin. Now, if you look at this table, okay, at 10 bar, and that's the S value. then you will know it will be just slightly below 50 degrees centigrade. So then you can calculate, and then we know that at 50 degrees centigrade it is 943. So at 50 degrees centigrade is 0.943 kilojoule per Kelvin. So turns out you're going to easily to calculate, then I will be slightly less than that. And then you just look at extrapolation, choose at 40 degrees centigrade. This is a 0.907 kilojoule per Kelvin. So you can assume like within this 10 degree change, you're going to have change 0.036 kilojoule. And so as a result, now in order to reduce by 0.003, so it's going to be 1/12 of the 10 degree. So therefore, T at the 2 is going to equal to 50 degree centigrade minus 0.003 divided by 0.036. So it turns out equal to 49.2 degree centigrade. So now, okay, so I calculate the point number 2 is 49.2 degrees centigrade. The next is, then I will be able to use this table again to calculate what is my enthalpy is. So you're going to find out it is just, again, you're going to use this table. It's going to be it's just a slightly below 280 kilojoule, right? So you can then calculate it and use this extrapolation, you can find out H2 turns out equal to 279 kilojoule. So now I got H2, I calculated H1, then what is H3? H3, remember H3, then I can come back and use this table, 4.3, 10 bar, and this is going to be at 39.4 degree Kelvin, and it's going to be at the liquid. So it will be at the H3 is going to equal to 105. Okay, so what do I get? I get H3 5 kilojoule. Then I can plug this in. What did I say? I said this is going to equal to H1 minus H3 and H2 minus H3, and H2 is going to equal to 279 minus, what is the H3? H3 is 105, and what is the H1? Minus H1 is 231 minus 105. And that is how you're going to get your coefficient of performance. So one interesting thing is that it will ask you is, say, okay, now you know this. You already calculate H3, right? H3 is going to equal to 105 kilojoule. Now, if you now bring it down to this point, which is at minus 26.4 degrees centigrade, will you be able to calculate in point number 4 what fraction become liquid and what fraction become gas? So then, if you want to do that, then you can do is to go to this at 1 bar. Okay, you know what is the enthalpy of the gas, what is the enthalpy of the liquid, and then you know you need the enthalpy to remain the same. So from 3 to 4 need to be the same. So you know 3 equal to 105, okay, and has equal to H4 has to equal to 105. But it's going to equal to some part of liquid phase plus 1 minus x of gas phase. And since the liquid phase and gas phase enthalpy are all given to you, so you should not have problem to calculate that. So that kind of end what I want to tell you about how do you use those table to calculate the coefficient of performance, and how do you calculate from the information, you know what the entropy, what the enthalpy is. And now in these isentropic process, you know enthalpy need to be the same. This is how you calculate the temperature there. And from here, okay, so this one become liquid now at 1 bar, and then now you have this thing go throttling, and you will be able to calculate what would be the fraction. What fraction is the liquid? What fraction is gas? Because now its enthalpy remain the same. And then you go look up the table, you can calculate that. So that's it.